What's this? Children asking for food, a general air of malaise, themes of dread and horror and death. That can only mean one thing. It's midterm season. Hey everybody, today we're talking about compactness. You might think you know a little bit about compactness already if you know anything about the real numbers. There's a theorem in your real analysis class called the Heine-Borel theorem, which says that compact subsets of Rn are just closed and bounded. That's cool, but it cannot generalize to other topological spaces. Why? Well, because boundedness is not a topological property. We already know that R is homeomorphic to the open interval 0 to 1, but 0 to 1 is bounded and R isn't. Basically, topology forgets about metrics and sizes and distance. So that means we're going to have to be a little bit more clever to define compactness in general. The idea is going to be to think of a compact set like A, B in R, and think about what sort of properties make this set nice to deal with. The answer is kind of tricky to stumble across on your own if you haven't seen it before. So let's define compactness together, and then walk our way through the definition to understand that this is the correct one to make. We start with the idea of an open cover. It is what the name says it is. An open cover of X is a collection of open subsets that cover X. We'll use these covers to define compactness. A space X is compact if every open cover has a finite subcover. And that's just a finite subcollection of the original cover that still covers the whole space X. Ta-da! There's our definition. Except, yuck. This definition is completely unwieldy. Every open cover has a finite subcover? How am I supposed to argue about every open cover? Showing a set is compact is therefore kind of a tricky thing to do. On the other hand, showing a set is not compact is relatively much more easy. You just have to cook up at least one infinite cover that doesn't have a finite subcover. So here's an example to calibrate. R is not compact. We may already know this from the Heine-Borel theorem that I mentioned before, but we can prove it straight from the definition of compactness. Consider an open cover A, which are a collection of sets that are open intervals from n-1 to n+1 for every n that's an integer. No finite subcover can exist, because every integer is only contained in one of these elements of the cover. Thus, every single set is necessary to cover R. Throw away any one of them, and you no longer cover the corresponding integer. Hence, here's an open cover with no finite subcover, and thus R is not compact. Okay, so we've said that in general, coming up with examples of compact sets is kind of tricky to do. So if we want to gain an intuition for compactness, let's do the next best thing. Let's start proving some results to calibrate how to think about compactness. For example, closed subspaces of compact spaces are compact. Let X be the compact space, and let Y be the closed subspace. We need to show that every cover of Y has a finite subcover. So let A be any old cover of Y. But Y is closed in X, so its complement is open. If we add Y's complement to our collection A, then this is now a cover of X. And we knew X was compact, so this cover has a finite subcover. Throw away that complement of Y if it still remains, and you now have a finite subcover of Y. Thus, any cover of Y has a finite subcover, and thus Y is compact as we claimed. Okay, we have a bit of a better understanding about compact spaces now. What would be really cool is if the converse were true, by which I mean compact spaces are always closed. That would actually give us a classification of compactness. Unfortunately, that's not true. We can actually cook up an example. Do you remember way back in episode 2 when we talked about the finite complement topology? In the finite complement topology, non-empty sets are open, well, when the complement is finite. Give R the finite complement topology. Let's cook up an example of a subset that's compact but not closed, because in this space, every set is compact. Let Y be any subset, and let A be an open cover of Y. Pick just one open subset out of A. Its complement must be finite, so that means we only missed n points from this one element of the cover. That means we only need to add in, at most, n more open subsets to completely cover R, and thus this subcover of Y is at most size n+1, which is a finite subcover. So every subset here is in fact compact, but not every subset is closed because this isn't the discrete topology. So the two concepts are in fact different. All hope isn't lost, however, because in a nice enough setting, we do in fact get the converse. Compact subspaces of Hausdorff spaces are closed. So we had to add in the extra Hausdorff condition. The example we cooked up with the finite complement topology wasn't Hausdorff. So let X be the Hausdorff space, and let Y be the compact subspace. We'll show that Y is closed by showing that its complement, X minus Y, is open. To do that, all we have to do is pick a random point inside of X minus Y, call it little x, and show that it has a neighborhood inside of X minus Y. Here's how we'll build that neighborhood of X. For every little y in Y, we can separate X and Y with disjoint neighborhoods because the space X is Hausdorff. Call each neighborhood of X U sub Y to reflect the fact that each one of them depends on the Y. And call the neighborhood of Y V sub Y, but set that aside because we'll come back to it later. Now, no single one of these U sub Y's necessarily has to live in X minus Y. So we're not done yet because we need a neighborhood of X that lives in X minus Y. We could try to take the intersection of all the U sub Y's, but that might not be a neighborhood anymore because it's an infinite intersection, so it might not be open. So remember the V sub Y's we set aside 2 sentences ago? Well, all of them have to cover Y, and Y is compact, which means only finitely many of them are needed to cover Y. So Y is covered by a finite collection of V sub Y i's, where I ranges from 1 to n. So now here's our neighborhood of X. Take the intersection of all the corresponding U sub Y i's. This is a neighborhood of X because it's a finite intersection of open sets, hence open. It also contains X because every U sub Y I does. But is it in X minus Y? Yeah, it is. If Z is some point in Y, then Z lives in V sub Y I for some I between 1 and n. So, correspondingly, Z is not in U sub Yi because the two are disjoint. Thus, Z is not in the intersection of the U sub Yi's. So, we squeezed a neighborhood into X minus Y. So, X minus Y is open, and thus its complement, Y, is closed, as we needed to show. Therefore, in a Hausdorff space, if you have a compact set, then it is closed. Ta-da! That's great! Here we see yet another reason why the Hausdorff condition is so nice to have. Limits are unique, singletons are closed, compact spaces are closed, and so on. The world is nice when your topologies are Hausdorff. Man, wouldn't it be awful if there was a really important topology that wasn't Hausdorff? Think fast, here's another theorem. If X is compact, and f from x to y is continuous, then f of x living inside of y is also compact. Easy peasy. Cover f of x by some cover A. Pull the cover back to x. X is compact, so there is a finite subcover. Push forward the finite subcover back to f of x. The end. Now your homework. Use this to show that if you have a continuous bijection whose source is compact and whose target is Hausdorff, then you actually have a homeomorphism. Neato. Everyone who comments gets 5 homework points. Okay, so now we more or less have an idea of how compactness might behave, And we also have a couple of theorems under our belt guaranteeing whether or not a space is compact. Now we want to build compact spaces. We want to see examples. We'll need another definition first. We say that a space is locally compact at X if X lives inside of a compact subspace C, and you can fit a neighborhood of X inside of C. And of course, a space is locally compact full stop if it's locally compact at every point. Here's the obvious example which you should automatically picture. Rn is locally compact, but of course not compact. Take any point and surround it by a closed box. That's closed and bounded, so it's compact by Heine-Borel. Then you can always fit an open box inside with dimensions half the size of the closed box, and that is a neighborhood of X inside of the compact space. Ta-da! For a non-example of a locally compact space, let's consider Q with the subspace topology inside of R. We need to cook up a point X where there is no compact space containing a neighborhood of X. Consider X equals 0. Suppose that there were a compact subset of Q that contains 0 and also contains a neighborhood of 0. Call it C for compact. We can squeeze a neighborhood of the form negative epsilon to epsilon intersected with Q inside of C for some very tiny epsilon. Now consider the inclusion map iota from Q into R. That's clearly continuous, and since the image of compact spaces is compact, that means iota of C is also compact. And since negative epsilon to epsilon intersected with Q is a subset of C, that means that negative epsilon to epsilon intersected with Q is a subset of iota of C by applying iota to both sides. And we also get that the closure of negative epsilon to epsilon intersected with Q is a subset of the closure of iota of C by taking a closure of both sides. But since iota of C is a compact subspace of R, by Heine-Borel, it's gotta be closed and bounded. In particular, it's gotta be closed already, so its closure is itself. And of course, the closure of negative epsilon to epsilon intersected with Q is the closed interval negative epsilon to epsilon. That means that the closed interval negative epsilon to epsilon lives inside of iota of C. But here we reach our contradiction, because iota of C has to be countable, while the closed interval from negative epsilon to epsilon is definitely uncountable. Thus, Q is not locally compact. Okay, so how does local compactness let us build compact topological spaces? The magic is the following theorem. Hold tight, because it's a doozy. X is locally compact in Hausdorff if and only if there exists a compact Hausdorff space Y such that X is a subspace of Y and Y minus X is a single point. In other words, if we start with X, which is locally compact in Hausdorff, then we can add exactly one point to make the space X union that point compact. This is appropriately called the one-point compactification of X. The proof is kinda involved, but pictorially quite intuitive. One direction is easy. First, suppose we have such a Y. We need to show that X is locally compact in Hausdorff. Hausdorff is simple. Since X is a subspace of a Hausdorff space Y, then X needs to be Hausdorff. And locally compact is pretty easy too. Let X be a point in X, and let Y be the point in Y minus X. By Hausdorffness, we can separate X and Y with disjoint open neighborhoods, call them U and V, respectively. Y minus V is a closed subspace of the compact space Y, so by Theorem 10, Y minus V is compact. And U, a neighborhood of X, sits inside of Y minus V. Thus, we've shown that X is locally compact. The other direction is the tricky bit. Suppose that we have a locally compact and Hausdorff space X. We will build the Y, which is the one-point compactification of X. As a set, Y is going to be X union a point, which we will call the point at infinity, because the motivating example to have in mind here is something like R or R2. We'll cook up the topology on Y by defining two types of open sets. Type 1 is those that are already open in X. Type 2 are those of the form Y minus C, where C is a compact set in X. Your homework is to double check that this forms a topology. Just do it from the definition and check all the cases. Once you've done that, go ahead and also show that X is a subspace of Y. It's certainly a subset, so your job will be to show that the subspace topology and the type 1, type 2 topology are included in one another. Again, knock yourself out with cases. It's routine to do, but it's more illustrative if you go through it yourself. As always, ask in the comments if you get stuck. The real meat is showing that this Y that we've built is compact in Hausdorff. So, for Hausdorff, pick 2 points in Y and we'll try to cook up disjoint open neighborhoods. If the 2 points you picked were in X, then we're done, because X was already Hausdorff. So, we just have to think about what happens if one of our points was infinity. Call the other one X. This is where local compactness of X comes in. X has a neighborhood U which sits inside of a compact set C. Then Y minus C is an open set that contains infinity, and U is an open set that contains X, and ne'er the twain shall meet. Okay, all that's left to see is that Y is compact. Well, cook up an open cover A. Since infinity must be covered, that means that one element of your cover is Y minus C for some compact set C. Since C is compact and A is covering C, that means that there exists a finite subcover of C. If we toss the open set Y minus C back in, then this is still a finite subcover, and it now covers all of Y. Hence, Y is compact. Hooray! So that's a one-point compactification for you. A couple of examples. The one-point compactification of R is the circle S1. The one-point compactification of R2 is the sphere S2. And if you think about R2 as the complex plane instead, then the one-point compactification is called the Riemann sphere, and it shows up all the time in complex analysis. And for good measure, the one-point compactification of an already compact set is just throwing in that point at infinity and declaring its singleton to be open.